And let's pick it up with number 3. Determine the parametric equation and the Cartesian equation for a circle with a radius 8. Okay. Examples. I've got this other thing ready now. Oh, don't use that pen, you silly. Okay. Determine the parametric equations and the Cartesian equation for a circle with radius 8 and center -3, 1. This thing's been moved over now. And that will change how the parametric and the Cartesian equation go together. Now, if you're at this point going, I'm not even sure I know how circles work exactly with either of these things, this is where you need to get to, being able to do what I'm going to do here, okay? To be able to go, okay, over here I'm going to go, first I'm going to go after Cartesian. I don't know which one's easier. I think you'll probably find the Cartesian's easier right now because it's more familiar, and once you get better at parametric, you'll find them easier than actually Cartesian. But the Cartesian equation, here's what you should be thinking. This is the part you're going to need by the time test comes around. When they start Cartesian equation of a circle, you should be thinking first, x squared plus y squared equals r squared. And I'll call that new information today, even though you did see it in 10 academic in one random day. Then you see that the center's -3, 1. The next part of it is to go, oh wait, that's not right. No. It's going to be x minus h squared plus y minus k squared. I've used the official letters in the exact spots that textbooks usually do. You don't really need that. What you have to know is that I've got to transfer this thing. I've got to move it around. And it works like the other transformations you've seen, is that I've got to go x, and I need the center to be at -3. So I've got to move left 3. So what I put in here is +3. Does that fit a little bit with your knowledge of transformations before? That's the opposite of what you expect it to be. We act like that's completely normal. We go, oh yeah, it's the opposite. No big deal. But it's completely whacked that it should be like that. And the reasons it's like that is because the number's right with the x. It's not over on the other side of the equation where it should be adding on to the x, so it's got to be backwards. And then this one, the y value, I want to go up 1. So this is going to be a -1. Now, if that freaks you out, it should. You're like, wait a minute, no, the y values were normal. When we did it before, the y values were normal. No, that's not actually complete knowledge. It's whether it's in with the x value or outside the function. That was the important thing. Whenever I taught it, I tried to say inside, outside. Inside, it does the opposite of what you might think. Outside, it sort of does what you think it would do. So this one's inside the brackets again because it's a weird equation. Now what goes over here? R squared. What was the radius? 8. And I'm going to write 8 squared. And you can leave it as 8 squared if you want. It's fine as 8 squared. But really, most times when you see it, you'll see it as 64. And this is another example of not trying to get it down to y equals. This equation's better implicitly, is the fancy word for it, where you got all the x and y's, but it's not y equals. There's where you need to get to with Cartesian equations of circles, is the ability to go, okay, I can manage different radiuses and different centers. Today, no. When you do your homework, somewhere along the way, you got to get to that point where you can handle that. Then, new, parametric. Here's where you got to get to with parametric equations of circles, where you can go, okay, x equals a cos t, y equals a sine t. So if you're making up a study page for all this, you're going to write down Cartesian circle, boomba. Parametric circle, boomba. Yeah? You're like, oh, I don't make study pages. Yeah, you're going to have to grow up, I think, probably. Yeah? Study pages are where it's at. Get it all on one page. Fancy colors, crazy highlighters. There's got to be somebody in here. Carries around 46 different highlighters all the time. Yeah? That's a great way to handle it. You should see this crazy stuff that my daughter Bella does, just to be able to not memorize it all. Once you're at university, memorize it all. Memorize as much as I can before the midterm is where you're at. Okay. That's where you got to get to with parametric equations. A cos t, A sine t. I'm going to ignore this for a second, okay? Because this is sort of new, and I'll deal with that in a second. And actually with parametric, it's so nice what you have to do there. So, in this case, it would be x equals, what was the radius again? 8 cos t, y equals 8 sine t. If you missed that part or you're confused a little bit about why that produces circles, go back to that investigation. The investigation in the PowerPoint there walks you through it and go, oh, look, it becomes a circle. And then I did the development of it algebraically to say, yes, it is the same thing as a circle. One thing I missed, though, yes? Moving the center. This is a circle, radius 8, but centered at the origin. If you want to move it, okay, you're going to like and hate what I'm going to do next. You're going to like it because it's simpler than with the Cartesian version. You're going to hate it because it's different than the Cartesian version. To modify the x, you just take the x value you had, and you've got to move it -3. And you take the y value you had, which was 8 sine t, and I've got to move up to +1, so I've got to move up 1. Which, if that doesn't explode your brain, it should explode your brain. That's the right place to be right now. It's like, what? You're changing the rules. Let me redefine the rules again. Let me say the rules again. When you're shifting things around and you're inside the bracket with the x, you got to do the opposite of what you think you're going to do. If you're over here on the other side, away from the x, it does what you think it would do. Parametric does what you think it should do. You want to change the x value, take whatever x value you have, and subtract 3. That makes perfect sense. It's what was happening before that didn't make any sense. Because of the Cartesian, we had those numbers buried in with the x, which is not the greatest place for them. If that's still a little screwy in your brain, that's okay. I would suggest that the percentage of people who really get that and don't just memorize it is shockingly low. Start with memorizing it, and every time you look at it, think about it and go, why is that happening? First, the first beachhead to establishing the understanding between them is that these numbers are with the x, these numbers are on the other side of the x. So they have to be opposite somehow, because they're not in the same spots in the two versions of the equations. Okay? You don't have to be here yet, but I hope that example crystallizes where you got to get to, what you got to be able to do. Okay? Questions there? I'm going to keep going back and forth with the PowerPoint because I know the PowerPoint jumps from examples to other things. Oh, a new shape. New shape. The question a few minutes ago that I planted in someone's, I did the silly voice. I go, what if the numbers aren't the same? 3 cos t, 4 sine t. How are these equations different from those that represent a circle? Well, the answer to the first question is easy. And I'll use the fancy words. The leading coefficient in x and y are different. Ooh, I like how this pen writes. It's better than the other one. Use a calculator to graph the curve. Oh yeah, sure. Why don't graph the curve? Let's get the. Here we go. Here we go. Here we go. I've got my nice window there. Now you got to be careful when you switch from one example to the next because you've played around with the window settings a little bit. Okay, so I got to do a couple of things as I go through this. First, back into menu. 5 for graph, F6 to get back to the equations. And I don't like playing around with the old equations. I'm just remembering that from last year. You might be good at editing the old equations. I'm not on my computer screen here, so I immediately go F2, F1, and I delete the old ones and go, let's start again here. 3 cos t. And then 4 sine t. Now, the only thing, I'm not going to press the button yet, because I'm not sure I'm going to get exactly the right thing here just yet. Because I played around with those t parameters. So I might only get, I forget whether I was on a half or a quarter. You know, I might not get all the t values. Because this says go back to 0 to 2 pi. So in my mind, I'm going to hit draw. I'm not going to really look at the graph there for a second. Okay? I'm going to immediately go V window. And I'm going to go down to the t theta and t max and go t theta 0, t max 2 pi. So if you're making some notes on, did it take 2 pi? No, it didn't. 2 pi, enter. There, that's right now. Now, exit and go to the graph. Zoom out is your friend here. Yeah, I got a nice window. I can sort of see what's going on here. I'm going to go to zoom and just go zoom out. Interesting. Interesting curve I'm getting this time. I'm going to get to your question in just a second. I hope you saw all that. Some of that's just getting used to the calculator, right? You know, and getting used to how you type all these things in. You have a question? This button here, x theta t, if you hit that, it looks like it's going to do x. Oh, because you're not in parametric. Okay, so again, that's all in the video from today. Before you even start, we got to go to type, and today we're doing parametric equations. So that's one of the first things we did today was go over to parametric equations. Now it should work. Okay, good. Notice that I'm not picking on you, Owen, actually. Not that I won't. I will. Go ahead and pick on you. You missed the first part of this lesson. And the nice thing about me making those videos is that later on, or even at lunch, if I get them up, you have to watch the first part of the video again and check it all out, right? Okay. Use a calculator to graph the curve. Okay. Just said graph it. Huh? See, how do the numbers in the equation relate to the graph? Now let's really look at the graph and see what we got here. And I really wish that B had asked what equation what you see there. And most people call that an oval. Yeah? In math, we call that an ellipse. I was just reading about this the other day, actually. I'm reading a book on the history of quantum mechanics, and they were talking about the history of understanding the solar system and whether the solar system, whether it was the sun was at the center, or the earth was at the center, all these things, and then the discovery that a planet's orbit in ellipses, these exact shapes here. It's not a perfect circle. I mean, we imagine it going around a circle, but the Earth actually goes out a lot farther in one direction than it does in the other. That's not why we get seasons, but it does have a slight effect on our orbit and everything like that. Anyways, ellipse. How do the numbers in the equation relate to the graph? Okay, it's not radius. I'm going to use the word radius here. The word is not radius. But just to incorporate what you've already got, it now sort of has a radius 3 in the x, but now it's got a radius 4 in the y, which actually clicks pretty good with my understanding. I go, oh, it's been stretched 3 this way, but it's been stretched 4 that way, which fits with all those words and all those things that we were doing before. And that's how we end up in the ellipse. And I saw a question. Where was it? Oh, yeah, because of the window. Okay, so in these situations, you got to watch to go, before you even start, go to a square window. And then zoom in, zoom out from there. Because with circles and ellipses, the stretching of the window can stretch you right back to a shape that you don't want there. Okay. Okay, so the words aren't radius. I used them just there, and I'm going to stop doing that. But how do the numbers relate to the graph? They are the stretch factors. And I'm going to get even better word for that very soon, but for now I'll use the words you already have. Stretch factors in each direction. That example should be pretty good. I hope that example, if you understood the circles, expanding to the ellipse is like, oh yeah, I can see how that would expand out to the ellipse there. Determine a Cartesian equation. If you had a seat belt in your desk, now would be the time to pull it on. Really going to do some math here. Not math that's beyond you, but a different kind of thinking here. Because we found out that cos squared plus sine squared is 1, that's a handy thing. When you've got coses and sines, it's like you immediately want to square them. Squaring will be good for cos and sine, because maybe they can get together. But it doesn't work here really well. It sort of works. Watch this. I'm going to start up here. D. I'm not sure what you want to copy down. Maybe you want to let me go for a little bit here. Let me go a little bit, and then at some point I'll say, okay, now you might want to copy, okay? X squared plus y squared. What do I get? I got 3 cos t squared plus 4 sine t squared. Oh, this is when you know you've got into the right field for you, by the way. I'm into math. I've done this example millions of times. I don't know how many times I've done an example like this. I just got chills about what's about to happen here. It's so good mathematical-wise. I just had this talk with my son Max. He's good at math. You're all good at math and everything. He's taking AP math, whatever. And I said, I don't care one little bit if you take math ever again. It's irrelevant to me, unless you like it. I like it just as much as you like it. I like it for him just as much as he likes it. Find the thing that speaks to you. Yeah? If it's math, great. There's so many options in math, and it's only going to get bigger as far as the options down the math pathway. But if at some point you realize this is not your thing, yeah, finish the course, whatever like that. But make sure when you're doing course selections for next year, you choose something that does speak to you up to a point. We don't get paralyzed in this desire to find something that's perfect for you to the point where we're living in our parents' basements at 35. Yes? At some point you go, well, okay, maybe I haven't found the thing I love yet, so I better take something I like so that I can, stop eating crap dinner in my parents' basement all the time. You know what I mean? Like, you got to move on at some point. All right. Okay, here we go. Back to here. Okay. Square everything. This worked before, right? I hope you can see it's not going to work this time. Squared, 9 cos squared t. Everything seems happy right now. 16 sine squared t. Everything's happy. What was it that happened last time that allowed us to survive this? This came out to 1. The common factor got it down to cos squared and sine squared. There's no common factor that'll work here. If I common factor out 9, I'm going to have 16 over 9. If I common factor out 16, that's not going to work. There's no really good tricks here. If only this had played out, that when I got to here, there wasn't the 9 and the 16 there. Tried to lay the hint, so someone might be able to come up with an unbelievably simple and clever trick. Divide. Yeah, right at the start. It's not x squared plus y squared in the case of the ellipse. It's x squared over something plus y squared over something. What would you suggest x squared should be over to make my life beautiful when I get down to here? What's the number that's causing the big problem? Put that over 9. You're like, you're just making stuff up as you go. I'm like, yeah, exactly. X squared plus y squared didn't work. X squared over 9 plus y squared over 16. So this was over 9. This was over 16. This is over 9. This is over 16. And I get cos squared plus sine squared. And what's cos squared plus sine squared? 1. Let me just draw a line and show the Cartesian equation for ellipses. X squared over 9 plus y squared over 16 equals 1. I drew that a little fast and it's not as neat as I want it to be, so I'm going to fix it up there. My computer is shockingly slow. 16. Why did I write a 16 there? Huh. That's some mathematics. Finally, after 10 academic, 11 new advanced functions, now we're getting into some stuff where it's like, we can play around with this. We've got enough weapons available that we can do some math. And ellipses aren't irrelevant. They're not ovals. These are the orbits of the planets. In your lifetime, you guys better get out there. We're screwing up this planet. We better figure the other ones out. Any questions about that monstrosity? I did not make you make that jump on the test. You can still survive by going ellipses, parametric looks like that, Cartesian looks like that, and you can survive with memorization. it might be worth it. It might be less work to memorize than to try and work through this all the time. Yeah. I definitely do. I don't do this every time. I got the two versions memorized. It's in your notes. I'll get to it in just a second. Questions? All right, back to the PowerPoint. Just make sure I'm doing these things in order. Boom, a new shape. Consider the following thing. I did all that. Determine a Cartesian equation. I did all that. Brand new. 0 to 2 pi. So we went all the way around the oval. Just like the circle, if you don't use 0 to 2 pi, you can get part ovals if you need them. Introducing the ellipse. Here it is. Here's the actual description. I could have taught this in the opposite way. I could have said, here's what happens with the ellipse. Memorize this, and then showed you the example. The ellipse has two axes. It has a major axis, which is always the bigger one. It's not the one on the x. It's the bigger one. Makes sense. Major axis. And it has a minor axis. These things aren't called radius. They're called major axis and minor axis. So for a and b greater than 0, you need a and b greater than 0. This is what I was talking about here. This is nicely divided underneath. The a and the b get divided there. There's the parametric version. The center is at 0, 0, but you can transfer this just like you do circles and everything like that. You can move them around, no problem. The length of that axis, if a is greater than b, the major axis is horizontal with length 2a. So that a is just like the radius. It's not, the word isn't radius, but the whole axis has length 2a. It's like diameter versus radius. The axis is twice of that. Yeah? To me, that's all pretty good, but do you have any questions about all that? They did it this way, with the a inside the brackets, so that a matches right up. So if I was to do it with their example right there, then I would have gone like this: x over 3 squared plus y over 4 squared equals 1. You can do it that way as well. It doesn't matter where you put that 3 or 4. You'll get there either way. So if you memorize and do it that way, you'll have it like this. If you do it from the parametric, you might end up with it like that. But they're the same. They mean the same things. You open. An ellipse. Say it one more time. Yeah, it's... I'm going to sidetrack me here. I love astrophysics. The ellipse, it works like that because there's focal points here in the center there that basically are the planets, and that's why because the planet is involved in the whole system, so that's why it goes out in an ellipse instead of a circle, because it's not just orbiting around there. It's sort of, the two planets are involved. And then you put other planets in here and the whole thing sort of, especially something like the sun, which its gravity affects everything in the solar system, so yeah. Great stuff. Oh, more examples. Okay, back to examples. Example 1, is that the next thing on? The numbering's weird here. Yeah? Determine the parametric equations and the Cartesian equation for an ellipse centered at the origin, major axis of length 9, parallel to the y-axis, and a minor axis of length 4 parallel to the x-axis. Okay. After all those examples again, you're like, I don't know where I'm at with these ellipses. Here's where you got to get to with ellipses. They want the parametric and Cartesian. So I'm going to do them separate again. I'm going to do parametric over here. And then I'm going to go after Cartesian. And I'm going to approach it the way I think that most of you should as you prepare for this test. Not in that development I just did with the cosines and sines and everything like that, but just as a memorized thing where you know the two versions of this. Now, over here, a little drawing of my ellipse. Major axis length 9 parallel to the y-axis. And I'm going to really exaggerate it here because it's major in the y direction. How's my drawing? Is it good enough to see its major's y this time? And that major axis has length 9. This minor axis this way has length 4. That's going to come up in the middle of all this. Okay? Oh, and I'm glad I'm doing the parametric first. I like the parametric first. Here's the parametric equations of an ellipse. This is where you got to get to by test time, where you go, oh, ellipse? I'm good. X equals A cos t, y equals B sine t. See how close it is to the circle? Just different stretch factors. Not a whole lot of extra memorization here for parametrics. And in this case, x equals, okay, what kind of stretch factor do we have in the x direction? 4 is the length of the major axis. So 2 is the number we're looking for. Did that little jump scare anybody? 4 is like the diameter. What we want is that 2, that radius. It's not a radius, but we want that radius part. And then y equals 9 was the stretch in the, sorry, 9 was the length of the major axis. So that stretch is the 4.5. You could then do your x squared plus y squared, figure out how to modify it all, do sine squared plus cos squared t, all that. You could do that to get to Cartesian. I would say most people don't. What they write down over here in Cartesian is, okay, x over a squared plus y over b squared equals 1. I think that's the way most people handle it. And not just like, oh, because you're in high school, you're just learning about it. I don't think so. I think people memorize both versions of this. And so what's the a here? 2? And the y is, or the, sorry, the b is 4.5. That's where you need to get to with ellipses, where you can write down the parametric Cartesian, bang, pump them in there. R squared is for circles? He asked a great question. Let me review that. As similar as the ellipses and circles are, the ellipse has a 1 over here, and the a's and b's are there underneath the x's and y's. But in the circle, x squared plus y squared, the r's over there. It's not a 1 over there. Things have been moved around a little bit because of the differences between the two shapes. That was example 1. Now I'm example 2. Yes? Oh, I got 20 minutes to land this plane. You gotta be done by lunch. Yeah, I think my plan's evolving. I think I'm going to try and be done by lunch. Give you lunch and a full work period to work on parametrics. And then I'll try and sneak another lesson in at 1:45. I think it's a much shorter lesson. Question? That's right. The A's and the B's, they're like the radius. I don't like using that word because it's not a radius, because the radius is only for a circle. But it's only half of that axis, not the whole axis. Sort of like in circles, we used r for the r squared. We didn't use the whole diameter. But they'll give that major axis in that whole number, that whole axis, not the A and the B. The A's in there. I think the PowerPoint has a good visualization of that. Yeah, right here. Do you see? A, negative A, B, negative B. That sort of crystallizes where the A's and the B's appear. Although the A's and B's can switch from, the A's are on the major axis, they can be this way if they have to be. Yeah? Determine the parametric equations and the Cartesian equation for an ellipse. Okay, after seeing the last example, we're like, okay, I sort of have a feel for that. But now they're giving me the points instead. It passes through the points negative 5, 5, 1, 5, negative 2, 2. I need some help here. Hang on. I got to go find it. Ah. Yeah. Copy. Back to, where was I? Here. Okay, a side speech about graph paper. Graphing isn't going away, folks. It's only going to get worse. You can see whether it's me or whether you're a disciple of mine or somebody else's, she's writing right in a graph paper notebook. It's a great way to handle this graphing problem. How many times are you scrambling for some graph paper? I encourage you to buy a, see if I have one here. Oh, that was close to getting feedback. I can hear it. When I started teaching AP Calculus, I started restudying some of my university stuff. This is like year 3 or something like that, because I was like, I got to make sure I'm a step ahead. You know, I don't want to be. Just so nice that when you're doing equations and so on graph paper, it actually makes my writing neater. If you have problems with neat writing, it keeps me neater writing. And then if I happen to want to graph, which I'm doing differential equations, so I don't have to graph, I'm right in my book like that. And they were on sale at Walmart for $2.50 or something like that. But it doesn't matter. You're using it for a whole semester. If it's $5, whatever. You saw I had to go looking for graph paper there. That's why I thought of it. Whoops. It's nice to have the graph paper right in your notebook. Anyways, here come the points. An ellipse with center -2, 5. Oh, I'm seeing that other point for the first time. That's not going to work out too well. Hopefully it'll work because I'll just add on to it here. Anyways, center at -2, 5. There's the center of the circle. And then I'll do the points in green instead. And passes through the points -5, 5, 1, 5, -2, -2, yes, and -2, 12. Okay, well, that's a little off my screen, but I think it's enough that I'll be able to get the information I need to here. There's the ellipse. Okay, that's not a great drawing, but I got to tell you, for me, that's pretty darn good. Yeah? So, to avoid the confusion that happened last time with major and minor axes, you might want to just do this and just put on the things that sort of are like the radius, right? The radius is sort of 3 this way, and it's sort of 1, 2, that way it's 1, 2, 3, 4, 5, 6, 7. Do you agree it's 7? Did I count that right? 1, 2, 3, 4, 5, 6, 7. That's all I really need the diagram for. To get that X stretch and to get that Y stretch figured out. 3 and 7. Major axis 6. Sorry, major axis 14, minor axis 6. Now I'm ready. What do they want? Parametric and Cartesian. Here I go. Parametric. X equals A cos t. Y equals A sine t. That's where you got to get to. I'm going to make a mistake, by the way, in the middle of this. So, not a mistake. I'm going to forget something. So if you notice it, great. Oh, that was. I was so busy bragging about the thing I was going to miss. I forgot that. There's B. Okay. X equals A cos t. B. Y equals B. Good. So the X stretch, if you want, that A value is a 3. X equals 3 cos t. Y equals, the stretch this way was like a 7. That's a 7 sine t. Good? No, not good. I'm missing something. I'm going to come back to it. Yeah? Cartesian. You got to get to the point where it's like, oh, Cartesian. X over A squared plus Y over B squared equals 1 for ellipses, yeah? And then so it's X over 3 squared. Why are you writing so weird, Mr. Todd? Because I'm getting ready for something here. Y over 7 squared equals 1. What did I miss? Still doing the smile thing under my mask like you can see it or something like that. What's missing in the whole thing here? Veronica. Yeah, the center got moved here. So, in the Cartesian, it does what we're used of, which is crazy. The fact that we use the opposite numbers here. The center's at -2, so I put a +2 here. It's been moved up to 5, so I put a -5 here. That is crazy, but we're so used to it, we think it's normal. But the parametric doesn't have those kind of problems. You want the circle to be 2 less on the x, you just go -2. There. You want the y value to be up 5, then you do a +5 there. So that's a weird thing to have to memorize. It's nice about the parametric. It's a nice feature of it, but it's different than what you've been pounding away on for a couple of years here. Yeah? You open. Bigger one's major, smaller one's minor. Doesn't matter if they go x or y. Yeah? Something sort of implied in the words. Major, big, minor, small. I got 12 minutes, do I? Parameterizing lines. We can also do parametric equations of lines. It's very convenient to parameterize lines. And that picture will become clear by April why we want to parameterize lines as well. You're like, I was fine with y equals mx plus b. Why would I want to parameterize them? Well, we can also parameterize lines. Can you see how this line segment shown on the right is represented by the following equations? Well, if I sub in 0, I get 0, -5. If I sub in 3, I get 6, 7, which is the endpoint. So you can do it with lines as well. Compared to ellipses and circles, it's actually pretty straightforward. And coming up with the equations, I don't know if I really got a system for parameterizing lines. I just sort of play with it until I get what I want. You know? Oh, last two examples. 11:35. Got to land this plane. Stop over-explaining. Examples. Consider the following parametric equations. X equals 3t, y equals 2 minus 2t. Here's your hint that you'll know it's going to be a line. When they look linear, there's no squareds, there's no sines, there's no cosines. You're like, okay, this is probably just a line. It's a complicated setup of a version of a line. It says sketch the graph of the relation. Oh, I need that graph paper again. Is it still in there maybe? Let's see if it's still in the... oh, yeah. Okay, you might have to sub in a bunch of points when you're first learning about these to know it's a line. I know it's a line because it doesn't have squared signs or anything like that. So all I'm going to do is sub in 2 points. I'm going to go, okay, here's my table of values. Table of values looks slightly different. I'm going to go t, I'm going to go x, I'm going to go y. I'm going to select a couple of t value, a couple of parameter values, dummy values. It doesn't matter what I use. I'll get the shape either way. Why wouldn't I just use 0 and 1? I would use 0 and 1. Yeah? Those are nice, easy ones to sub in. If I sub in 0, I get 0, 2. I'm doing that very quickly. I hope someone's checking me. Sub in 0 for x, I get 0. 2 minus 0, yep. And then I sub in y, I get 3. No, not 1. Sub in 1, I get 2 minus 2 is 0. Oh, I got the intercepts. Isn't that interesting? I didn't expect that. So 0, 2. 3, 0. Not convinced it's a line? Hey, it's a dummy variable. Put as many as you want in. Put a 2 in there. Put a 2 in there, I get 6. And -2. By then, hopefully you're convinced. But if you need a couple more points, good. As many as you want. Draw the line. Help me draw the line. Draw the line. Oh, arrows? Is it arrows? Do I put arrows in the ends? Yeah, negative infinity to infinity. It's saying this thing goes out forever either way. B. Use the different. Oh, yeah. Okay. Use the. I want to do a little bit of work here while you're copying. Lock that. Grab that. Put it up there. Buy myself some space. And we're going to rewind the clock because this is a test question. Put the big green star out there going, hey, yeah, I'm going to have to do this. Take some kind of parametric equation and switch it over to Cartesian. Will had the idea earlier. So whoever we're going to ask, it's not going to be Will. what do I do to these situations? So I've got x equals 3t, and I got y equals 2 minus 2t. What am I going to do with these things to end up with only x's and y's? Just solve for t in one of these things. You know, that's what's so nice about calculus. You know, look back on substitution and elimination in grade 10 academic and go, oh, why was that such a big deal? It's just one of those weapons we had to give you to be able to get to this point where we can do all sorts of great stuff. Which one's going to be easier to solve for? I think the first one. I'm just going to do a little rearranging here. X over 3 equals t. Sub t equals x over 3 into y. Y equals 2 minus 2 times x over 3. A couple of moments later, I've got my old friend. I've done this really fast while talking, so let's make sure I haven't made a mistake. It looks beautiful to me. My old friend y equals mx plus b, yeah? I can even look at my graph and say, is it right? Y-intercept 2, down 2 over 3, yeah, I got it. Okay. Now, your question, if you're really with me, is, well, then why did we go through all this? We had y equals mx plus b. You'll see big advantages to parametric coming up during this year. Okay? Or you can think of it as, well, let's practice on some easy ones so I don't have to do the cycloid, because you saw how crazy that cycloid got. Yeah? Any questions about lines? Is there one more? In 5 minutes before lunch? Consider the line segment with these endpoints. Find a parametrization. This is a little more difficult because they don't have a specific procedure on how to come up with this. If you have trouble with these, I suggest building the table of values and doing some thinking on the table of values, because your old weapons of thinking will help you here. They say we want the parameterization to go from 0 to 1. And I want to start with -2, 1 and end up with 3, 5. Notice this new word, line segment, which means it's just a line segment. It doesn't go on forever. It's just from here to here. So then you got to do some thinking about what x and y would have to be in terms of t to make this all happen. But you can use your old thinking. See, x starts at a value of 2, or -2. So I could go start with a -2, and then whatever I have with t isn't going to matter, because if I sub in t equals 0, I'll get -2. I hope you're sort of with me going, let's just sort of make this work out. And then what's the slope here? It's going up 5 for every 1, so I think a slope of 5 will work. Let's check it. Like, I don't want to make a specific procedure here. I want to just say, just make it work out. Yeah? Let's just check. If I put it in t equals 0, 5 times 0 minus 2 is -2. I get the x value I want. If I put in t equals 1, I go 5 times 1 is 5 minus 2 is 3. I got it. But don't overthink it too much. Just go, okay, what numbers is going to work here?
Good morning, everyone. This is Tony Eric. I'd like to just have everybody's attention to our grade 9 in particular, before we break for lunch. What we are doing, and this is for the grade 9 in particular, is the cafeteria is open, as I said on Tuesday, and we can incorporate 60 students in the cafeteria, so that's specifically good for our grade 9 cohort. And the other thing that we're instituting now, effectively immediately, is that when students are on their lunch hour, certainly they can stay on the campus if they go outside, but they're not using the front grassy area nor the sidewalk. So if you want to stay outside, you just want to have a seat, certainly go to the back field by the two parking lots, there's a large grassy area there. We do, however, make it clear that everyone must social distance. So if you're sitting on the ground or standing, make sure that you are maintaining the rule of 2 meters between everybody. Please be respectful of that. We would appreciate it. And certainly remember that everyone should be back in the class no later than 12:15, ready to go. So we'll, before we depart, we'll be grateful for the young from the Father and of the Son and of the Holy Spirit. Amen. Bless us the Lord of these ideas, which we bless through Jesus, my bearing, in Christ the Lord. Amen. In the name of the Father, and of the Son, and of the Holy Spirit.
I'm not ecstatic that I didn't over-explain that, but I'm sort of happy too. I want to leave that. I don't want to over-explain that. I want to be like, with lines, just play around, get the numbers right, get the right slope. So maybe start there with the slope and go, okay, I got to go up 5 for every 0.5, so that's up by 10. Where it's going to start, and just play around with those numbers. See if you can't play around with them and get them to go. If they don't go, if they're not going for you, come and see me, and we'll come up with a procedure for it. But I don't think you really need one for there. Any questions here? I'm going to ask permission to start teaching at about 1:30, I think, giving you your lunch break, and then when you get back, lots of time to work on parameterization homework. And then at 1:30, I'll go, let's get going. Let's knock this thing down, so maybe I'll be done shortly after 2, and then we can relax going into 2:55 at the end of the day. Good? We'll wait for the bell so that we don't get VP's attention. But on lunch break, your choices, to be clear, are just sit here. I'm going to sit here. Just stay here. Or grab all your, whatever stuff you want, and go inside, walk down to Hortons, take a break. But again, we're back at it. Should be back in class by 12:10, 12:15, something like that. And then I'm not teaching again until 1:30.